Hi, everyone. I welcome you all again on another podcast on computer vision series. And this time we have an expert from the field of 3D object detection, Mr. Darren Tsai. He received his BS degree in electrical engineering with first class honors from the University of Sydney, Australia in 2020. He is currently working towards his PhD degree at the University of Sydney. His research interests include computer vision and deep learning with a focus on unsupervised domain adaptation. I personally met Darren Tsai at one of the leading robotics conference, ICRA, 2023, which happened at Excel London, and then we met there and we thought we exchanged our ideas, and then that's when I thought it would be really good for our viewers to have a podcast from Darren Sai to understand more about his research experience in the field of unsupervised domain adaptation. So without wasting much time, let us go ahead and listen to him and learn more from his research experience in unsupervised domain adaptation and 3D object detection. Okay, good. Thank you so much, Darren, for accepting the invitation, first of all. And we are happy and delighted to host you today under the SciTech Talks. So, first and foremost, can you please introduce yourself and tell us your journey and motivation to get into the field of computer vision? If we would like to hear that first. Yeah.
Yeah, sure. So my name's Darren. I'm a PhD student from the Australian Centre for Robotics in Sydney. And I mainly focus on 3D object detection and doing unsupervised domain adaptation for it. So I've basically finished my PhD now, so I'm kind of in a transitioning stage to my next job. So the main, I feel like this field kind of got me interested due to being in my undergrad. I did electrical engineering, and none of the subjects really interested me until I actually hit one of the computer vision subjects, and that just sparked a real interest in the topic. And so also coupled with my I really dislike driving, and so that kind of I was thinking a lot about autonomous vehicles here and there, and then one day I just saw and like in our group we have like an autonomous vehicle, like it's all like stickered on and it's like driving around campus. And one day I just saw that and I was like, you know what, maybe I should contact this group. Contacted them, and then they took me on a tour around the lab, and then that was basically how I got in. Um, yeah, and it's just really interesting because it just opened my eyes to the whole new world of like robotics, which I didn't even know was. But yeah, since then I come to focus more on like 3D object detection, and then we realized that when you just try to deploy once a set, and it also really helped at that time that I was working with like a LiDAR company that had adjustable scan patterns, and it just didn't work out of the box. And so that was kind of what I delved into and trying to figure out why did it work. And then it opened the doors to this topic called unsupervised domain adaptation, because we didn't want to spend budget on labeling data to train the detectors again. So yeah, that's just a bit about myself.
Okay, that's I think that's the most organic way of getting into this field of computer vision. I think, yeah, you see
Yeah,
something and get inspired and then get into that field. I think, yeah, good.
definitely.
So,
Yeah.
yeah, and good to know that you're more into 3D object detection. I see there's a lot of scope to contribute in that field in these days. And can you please briefly introduce us what is 3D object detection and what sort of challenges that you might encounter in this? And can the say I majorly work in 2D object detection. So
Mhm.
how easy or difficult for us to is that how easy or difficult for us to adapt those 2D object detectors? See, 3D for me is an extra dimension that out of
Mm.
along with 2D, right? So now, how easy or difficult for us to use those 2D object detectors and extend to for 3D object detection?
Yep. So 3D object detection, the main task is to estimate the center of the object in 3D, as well as the dimension of the object, and then what the heading of the object is. And this is quite different to 2D, where a lot of the times you don't have an oriented bounding box, but you just have a axis-aligned bounding box. And so in 3D, having that depth aspect is more like there's more parameters to estimate really. In terms of the architecture design though, a lot of the 3D architectures follow 2D architectures. You also have the one stage and the two-stage 3D architectures that you typically see in the 2D, and they kind of follow a similar, I guess, design as well. The main contributions for a lot of the work that I've seen mainly focus on how you best represent the point clouds. So, like, say, for example, there's a popular work called PointNet where they figure out how to basically manage the unordered nature of the point clouds by using like a max function. Or there's other works that try and voxelize the point clouds, which is one of the more, I guess, mainstream works by voxelizing point clouds. Because when you voxelize them, you can get them into a regular grid, and then that's quite similar to just using 2D images, where the pixels form a regular grid. So that's more of a straightforward thing. Um, and in terms of the challenges that differ between the 2D and the 3D, one of the things is that LiDAR is really sparse. And so it's different to pixels where every grid cell has a value. In LiDAR, certain voxels may not have anything at all. And certain voxels may only have one point, and that point may be the only point that you get for the object. So then, especially if the object is, say, 50 or 70 meters away, and you only have 1 to like 10 points for the object, you're still expected to estimate the size of the object. And that's really hard because how do you know how long a car is if you only see the back of the car? Even if you had 100 points, if you only see the back of a car, how do you estimate the depth of the car, let alone the orientation? Because let's say you have the back of the car like that. You don't know if the car's facing there or there. Like it could be a whole bunch of different directions. And that's quite challenging for this task. So yeah, that's one of the main challenges, I think.
Mm. Okay, okay, that's interesting. So LiDAR, you say that LiDAR is very sparse, and that's one of the major challenges. And how about the LiDAR performance when compared to other ways of getting the 3D information? Say, I used to have a course called Multiple View Geometry in Computer Vision during my PhD days, and
Mm,
it all talks about extracting the 3D information from multiple views. And even say, I heard that a couple of years back, Tesla cars have removed the LiDARs from their system, and they wholly rely on the views that they get from multiple cameras, right? So,
yep,
in what way LiDAR? So, can you please compare these two things? Is what
yep, yep.
I wanted to know. Yeah.
So I'll address the Tesla one first. Because when you work in the autonomous driving field, everyone's like, do you need LiDAR?
Mm,
But anyways, for Tesla, they estimate depth from their cameras, and that requires more it requires more algorithms to estimate depth. And a lot of these algorithms actually use LiDAR as the ground truth for the estimation of depth. And so
mm,
I guess the counter argument is why would you need that if, let's say, you can already use a LiDAR sensor? Also, in conjunction with that, the LiDARs are getting pretty cheap nowadays. You can get like a decent LiDAR for around $4,000. And it's got more resolution than you would have about 5 years ago. And so that's the general trend of like the scalability of these LiDARs. And I think that
mm.
there's no need to like limit yourself to just using cameras and radars when you can tack on another one for security and robustness. And also, LiDAR sensors typically have much better 3D object detection at further ranges. So even though these cameras can actually like estimate the depth, it's not actually that accurate in terms of the centroid estimation and heading estimation of these objects. LiDARs can actually do much further ranges than these image depth estimators, and they can do it with much better accuracy. And also with LiDARs becoming more and more dense, you're having like, say, 128 beam, and you can stack a whole bunch of LiDARs to have much denser resolution. So you can go even further than a lot of these images. And so I just think overall, LiDARs are much more robust like estimator of 3D position. But with that said, images are a lot better for classification because you have the color. And overall, I think the general direction is headed towards sensor fusion anyways, where you have the classification and the localization as complementary. And that's where a lot of the 3D detection works these days are actually moving towards. Yeah.
Okay, thanks. But how about the performance of LiDAR in adverse weather conditions? Uh, and say something like a maritime industry, or if you want to develop an autonomous vehicle there, how would it perform? Or even on the roads, in say in UK, at least, right? So we do there's a lot of snow sometimes during the winter, right? Or foggy during the early mornings.
Yep.
So what's the performance of lidar in those scenarios?
Yeah, so the performance of LiDAR isn't fantastic when there's rain or snow or fog. It struggles to pierce through those kind of environments. And even in certain cases with black cars, it tends to have quite poor reflectivity. In certain data sets, you can see that when it shines, when there's a black car, a lot of the times you can probably see the edge of the car and some scattered dots here and there, but the car is mostly like invisible almost to the LiDAR.
Mm.
But that's also why I think that the future is towards some sort of sensor fusion approach, where like you can use radar, which is more weather agnostic, to be able to handle lots of different conditions, and then you can use camera when like there's sunny days, for example. But then camera also like suffers from like terrible reflections, and then in that case you can use lidar. So I just think that the holistic solution will include the use of multiple sensors to kind of complement each other, especially with the failure modes of these things. Yeah.
Okay, okay, okay. Yeah. So I got your point.
Yeah. You
So
also
so
asked about multi-view LiDAR, multi-view 3D as well.
yeah, yeah, multi-view 3D actually. How would you compare that with this basically?
So from my understanding of multi-view 3D, you'd have to like take different pictures around the object, right?
Yeah.
It's more of a different use case, I guess, because in terms of autonomous vehicles, you're constantly driving and you don't necessarily have the chance to take the multiple views around an
Multiple views.
object.
Yeah.
So in that case, with autonomous driving, when you take one snapshot of the scene, that might be all you get to work with in terms of the sparsity of the object. And so if, let's say you can get multiple views of the object, then you can really overcome a lot of the sparsity challenges with using LiDAR that we face in autonomous driving. So that may be a lot better to use 3D detectors just off the shelf.
Okay, okay. I got your point. So, but in terms of power consumption, what do you see? How do you compare these different cameras or different modalities to extract the 3D models?
Power consumption, I still think LiDARs are probably more efficient. This is not my strong suit because I don't really look into it, but
Okay, okay.
because with LiDARs, you have a 360 and you just need one LiDAR, whereas with cameras, you need six cameras and you need to manage the bandwidth of all the data processing as well. And so
Mm,
to do that, we typically, in my group, we have a separate computer that processes all the cameras for 360. And it's just,
mm.
there's too much information and you have to process them and do the depth estimation. It's a lot of work. So if you want a quick, snappy 3D detection of objects, I think LiDAR is probably your go-to.
Oh, okay, okay, I got you. But so, is that does it mean that lidars have lesser bandwidth when compared to the camera information that you get?
Well, they definitely take up less information because like pixels are extremely dense, whereas a LiDAR point cloud doesn't have that much like points compared to like using dense cameras for like we usually take around six cameras to get a 360. And so having like HD resolution or maybe less, it's still really, really dense information. Yeah.
Okay, okay, okay.
So
Yeah,
I
thank you so
assume
much for the
it's
clarification. Yeah, I think
that's all right.
that makes sense because majority of the listeners of this podcast would be the people who are getting started in this field of research in the field of computer vision. So that is the reason I start with some of these basic questions of the person who is there on this call.
Yeah.
So yeah, so that's all from the lidar point of view. So I just have now let's I just want to dive a little bit deep into your area of research. Darren, am I audible? Hello. Yeah. So,
Thank-
sorry, Darren. There was a
That's
disconnection from my end. Yeah.
all good.
Okay, good. So, but let's. We would like to know a bit deeper now into your area of research of unsupervised domain adaptation. for 3D object detection, basically, right? Um, so one of the problems I see in unsupervised domain adaptation, I worked in this area for last 2 years. Before that, I used to work in other areas of video object detection and those kind of an areas majorly. But I started researching more on unsupervised domain adaptation, domain generalization, these problems since last 2 years now. So one of the problem that I see is the negative transfer when aligning multiple domains, right? With a single target domain, and so what are the different ways in which we can eliminate this negative transfer, and what is the best approach that you think to eliminate the negative transfer when using this unsupervised domain adaptation for 3D object detection?
Yeah. So negative transfer, it's I guess the harmful reliance of like source data, and that kind of like transfers poorly to target data, right? That affects the performance overall in that transfer. One of the things that happens when you try and transfer from different target source domains that I find is a big one is label discrepancies. And one of the reasons for that is that your data might look almost exactly the same, but from your source and your target, you call it differently. Like for like a simple example would be like, say you had a man who's wearing a backpack. So in the source data, you might just label the whole thing as a man. Whereas in the target data, you label the man and the backpack separately. And that itself can be quite damaging to the learning of the model because the model gets confused. It doesn't know what to actually label this instance. And so one of the ways to mitigate this, I guess the simplest way would be like a simple remapping that to like a super category. Say if you have a label, if you have a man in a bag, just put it as a man. And just in general, if you have a man on a bike, just call it like the whole thing, for example. Just combine the labels is what I find would be an easy solution. Another way that I guess is the more hyped way that everyone is pursuing is to use large language models and just feeding these inputs to try and get similar feature vectors and see if these labels are more similar to try and align them to align different source domains. So that's one of the problems. Another one would be, say, if you had quite a lot of source data compared to your target data, then and you train them all together, then your model will be more biased towards the source. Just because you have a lot more of it, it's easier to minimize the loss for the source data than the target data. So one way to do this is probably like active sampling of the source data to try and balance it out with the target, or maybe you can try and devise some like clever loss function that can align them better to more of the fundamental stuff. Like for example, in 3D object detection, instead of learning the scan pattern, you could try and make the loss focus on learning the geometry of the objects. And that's a lot more common between the source and the target domains because geometry doesn't change too much. But then this could also be a flaw because in my field, there's a common problem in UDA where you have objects that are different sizes. So for example, if you train the detector in Germany and you test it in the USA, it would tend to predict cars as a lot smaller because European cars are smaller than the US cars. And especially when you can only see the back of the car in the point cloud, how do you know what the size of the car is? It will default to its statistical, I guess, learnings of what it has in its training data set. So that's generally the like a few kind of approaches for negative transfer. Um, Specific to what I think is the best for 3D object detection, I mainly focus on like say geometry or like temporal kind of methods. So I focus on using things that are common between the source and the target data. And in terms of the point cloud, in terms of 3D, especially object geometry is a lot clearer than say just using 2D images where you don't really have the geometry of the object because you don't have depth. And then furthermore, with point clouds, you can accumulate them over sequences, and that gives much better object geometry as well. And so, and also temporal consistency is a common thing for images and point clouds because time is just consistent in both source and target data. So that's generally what I lean towards for trying to filter out a lot of the like the negative transfer sort of thing. So I think that using source data is not bad. But it's more about how you mitigate this sort of thing with common features. So for my current work, I focus on using like the pre-trained detectors on source data, and then I just let them propose a whole bunch of different, I guess, objects that they think are there, and then using the temporal and also the geometry, I managed to filter them out to make sure that you have the cleanest labels possible. And therefore, I kind of have like an auto labeling pipeline for the target data. And then when I train the detector on this target data, then it directly learns the scan pattern of the target. So I don't rely on learning the scan pattern of this. I basically discard the scan pattern of the source domain. Unless it is quite similar in terms of appearance, then I'll just fine tune it rather than use the both of them together in joint training. So that's generally the approach that I find that works.
Okay, so you mentioned regarding the similarity, right? So how do you
Yep.
measure that similarity, or how do you identify? Is it like a manual process, or is there any very nice way of uh, where you have an algorithm which tries to identify the similarity? How that similarity is being estimated?
Yep. For LiDAR domain adaptation, it's a lot simpler. You can just visually assess how dense the point cloud is. Because there's a lot of LiDARs on the market, 30, you can easily see that 64 beam is more similar to another 64 beam than to a 32 beam. But
Mm,
the thing that you have to consider with lidars is that the beam configuration can be quite different. So you may have two 64 beam lidars, but they some lidars may focus towards the middle, like a dense horizon kind of focus, whereas others might be more separate and they might focus it uniformly. That could also be another problem for domain adaptation. But in the general case, I say that if you generally have a similar beam lidar, then I think it's not too bad to use for a baseline as a pre-trained weights.
okay, I got your point. Maybe it's the prime signature of LiDAR is the density, and that
Mm.
information you're going to utilize to determine how similar a target sample is to the source samples, basically. Yeah, I
Yeah.
got your point. Yeah, good.
And we haven't, I guess we like the domain adaptation is still quite in its infancy in 3D object detection. So we haven't actually got to the point in images where we are targeting the smallest things, like say a lot of the weather changes, like it's definitely important. And like there's a few papers in Waymo that target that, but that's for similar sensor as well. But I guess if you want to change your LiDAR to a different LiDAR, then it's a very different problem. And then you have to address the scan pattern as the biggest contributor. And then you also got the weather and all these other things, which might need a few additional techniques. But yeah,
Okay, okay. Got your point, Darren. Thank you so much for the clarification. And yeah, I was just going through your MSD, MS 3D plus plus. I think it's a very interesting piece of work, a very
yeah,
extensive evaluation that was done. So where is it going, or is it already published? I was reading the archive version actually.
yeah. I've submitted it to TPAMI.
Okay, okay. Okay.
Hopefully, I'll hear back. I don't know.
Okay, okay. All the very best. Looking forward to know your result as well.
Thank you.
So good. So it's an interesting piece of work which combines multiple different things for LiDAR and the unsupervised domain adaptation. It's a very extensive piece of study. When I was just going through it, I had a few questions on in terms of the detector ensemble that you guys have used, and you have a multi-stage training pipeline where you generate the pseudo labels and then use TTA basically to eliminate the noisy pseudo labels and then feed it back to the training pipeline. So uh, even though this approach looks very straightforward, I know how complicated the things are in terms of the choice of the detector that you should choose in an ensemble and the choice of the TTA approaches that we need to use, right? So, can you please share us some details about uh, how would you, if somebody wants to go is a detector ensemble kind of an architecture to generate multiple pseudo labels which agree upon each other, and so can what should be the how should be the how should one should select the detector ensemble, what sort of detectors they need to choose, or they just choose all the available detectors which are there in the state of the art literature, or what should be the choice of the detectors? That's the first point. The second thing is what are the different TTA approaches that you guys have used, and how are you in what do you say, filtering out the pseudo labels? If you can shed us some light on it, it would be very useful. Yeah.
Yeah. So for the ensemble part, it's a bit of a tricky one. Like if you had a small test set on your target data, you could identify probably the optimal ensemble. But then again, it's also not that important to identify the optimal one in terms of the average precision score, but rather you want to have the highest recall that you can get. Because that's the first part of the order labeling framework that I propose. And in the second part, we use like temporal consistency to filter out the false positives really. And so what we want is a really high recall in the initial ensemble. So in terms of what detectors to use, I would really like in for the study that we did in the paper, we looked at whether it was the architecture or maybe it was the training data, and we found that if you vary the training data, you probably get the most varied performance of the detector. So like I would suggest, say, using detectors that are trained on different source data sets. It could be the same architecture, just with a different training data set. And also, if you do vary, like say, for 3D detectors, I think the proposal head is quite important because that it's how they interpret the feature space and generate the box. And so some ways of doing that are anchor based, where you like it works for certain objects but not for others. And the other popular one is the center base, which is also common in like 2D works, right? You got the center net, and then you got the YOLO and whatnot. And so you got all these kinds, and I think that they give slightly different region proposals. And so those would also be good to kind of give more variation. And also, I guess in the more recent works, it'd be good to include more um, multi-sensor 3D detection networks because one of the challenges with just using LiDAR, especially for the cross-domain application, is that it's hard to detect, say, pedestrians. And if you could have a picture of what it is, you can easily tell that it's a pole or a pedestrian. Right now, I'm using the motion of the pedestrians to identify if it's actually a pedestrian or a pole. But if you had the image, then that prediction will be very possibly highly confident that it's a pedestrian. So that could really help as well. And also multi-frame detectors are also another thing that could potentially boost. So just, I guess, combining and seeing what works for your data set to get the highest recall as possible. Yeah.
Oh,
The second
okay.
question you asked was about
Yeah,
the like the filtering.
yeah.
Yeah.
Filtering the noisy pseudo labels and the TTA stuff that you guys have used.
Yeah. So the filtering, I touched about a bit about it before, but basically to filter out the false positives, we focus on static vehicles because it's actually a lot easier to like with a static vehicle, you have one position and you can actually use all these positions to confirm if the car is actually a car and if it actually is in that position. And so you just have so many times that you can actually just check if it's correct. Where if it's a dynamic vehicle, then the car's constantly moving. You get one shot and the car may no longer be there. So you can't actually tell if you got the correct car or not. Whereas with static, it's a lot more obvious. And then for pedestrians, false positives, if let's say I mentioned before, if the a pole can't move, right? A pedestrian can. And so pedestrians keep moving, but sometimes they stop at a traffic light or they and then they stop and then they keep moving. So you can label these pedestrians if they're dynamic. And then with the multi-stage self-training, you can basically teach the detector for the first round that these are what pedestrians look like. And in the next round, you'll be able to pick up more static pedestrians as well. And also for vehicles, because the vehicles are rigid body objects, when it's static, it looks the same as if it's moving. And so it can pick up the dynamic vehicles as well in later self-training rounds. So overall, that's how you iteratively improve the labels. And once you saturate it, then that's about it.
Okay, okay. It's more like going from a complex, sorry, the simplest and then the complex scenarios. Do you mean you are training your system in that way, basically?
So I'm not too sure what you mean by simple and complex. Could you clarify?
So what I mean is you start with moving pedestrians, and then is it like detecting the the static pedestrians, the people who are static, is it complex to detect? Is it for that reason you start with
Uh,
moving pedestrians and then going to a static ones?
well, so I do have static pedestrian detections as well. It's really whatever the source pre-trained detector chooses to detect. But the thing is,
Okay.
we only choose high confident detections of these objects. So I may also detect dynamic vehicles as well if they're highly confident and include them
Mm.
in the pseudo labels. The main point is that we want to increase the recall of like high quality pseudo labels and decrease the false positives. So in order to do that, like actually a lot of the occluded cars, or like if the pedestrian like appearance looks very different to the source data set, then the confidence score is very low. But basically, I use the fact that these pedestrians are moving to boost up the confidence. I basically just say, doesn't matter what the confidence is, if it's moving, just include it as a pseudo label. And in that way, it gets included even though it's below the threshold for what I deem fit as a pseudo label.
Okay.
That's the same
Okay.
with static vehicles too.
Okay. 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 Got your point. Yeah.
Oh,
Good.
good.
Yeah. Good. Yeah. So when I restarted it, actually, I missed pushing the recording button. Yeah.
That's
Good.
all right.
Yeah, no,
Like if you
no
want to go
problem. I,
through the
I
same
made a notes of
questions,
all these things. So I'm
great.
going to add them in the text. Yeah. Good. Yeah. Thank you so much, Darren. I think it was a very useful session that we had today. We started with your how did you your journey into the field of computer vision and 3D object detection, unsupervised domain adaptation, and we even talked about how expensive the lidars are and what are its advantages and what kind of value addition that it's going to give us in autonomous driving kind of an area, and the importance of identifying the negative transfer. How do we eliminate them? And especially in terms of lidar, those were some of the interesting points. And you also mentioned about how do you filter these pseudo labels in your recent work, which uses the multi-stage training kind of a pipeline, which involves several things like TTA and other stuff. And you even gave very useful inputs for the researchers. I'm going to make it in terms of the notes. And if there are any queries to the audience, they're going to definitely come back, maybe drop an email to you. It would be we would be grateful if you can if you see an email, and then if you can respond to for our audience, it would be very useful for them. Thank you so much for your time today.
Sure. Thank you so much. Yeah, it
Yeah,
was fun being on.
yeah, yeah. Thank you so much, Darren. And we'll see you sometime soon. Maybe if we drop down to Australia, we'll definitely catch up with you soon. Yeah,
Yeah, yeah, let me know. Would be keen.
yeah, yeah. Sure. Thank you so much, Darren. See you. Bye.
Thank you. See ya.